Welcome to the module on satellite detection of plastics. This module is divided in two main parts. In the first, we will explore how remote sensing methods, satellite technology, and machine learning are utilized to identify plastic debris pollution in the sea. We will delve into the fundamental concept and learn how satellite can detect plastic with the help of machine learning. In the second part, will be demonstrated how these concepts are applied by showing the tool that Air Center developed to detect suspected location of floating marine plastic debris in satellite imagery. Before we begin, I would like to introduce myself. My name is Andrea Giusti and I'm a project developer at the Atlantic International Research Center in Portugal. In my role, I work with geospatial data with a focus on ocean application. In this module, I will guide you through part 1A, focusing on the fundamentals of remote sensing for marine plastic detection. Following, my colleague Emmanuel will later take you through part 1B and part 2. So let's begin by understanding firstly some common terminology used in this field. Remote sensing refers to obtaining information about an object from distance. For example, photography is a simple example of a remote sensing instrument. Depending on the application, different sensor and method can be used, and the choice depends most of the time on the information which is needed, the level of the detail that is required, and how frequently the data is needed. Therefore, we can say that Earth observation, or shortly EO, is the process of acquiring observation of Earth's surface and atmosphere through a remote sensing instrument, which commonly result in a digital imagery that I believe you're all familiar with. Various platforms such as aerial platform, drones, and satellites can be employed, and each of these are offering unique advantages but also limitations. Aerial platforms provide, for example, a very high resolution imagery but are quite costly. Drones are more affordable but are quite limited by regulations and also by utilization range. Satellites, on the contrary, offer a reliable solution, especially because they give a global coverage most of the time, enabling regular observation even in areas quite difficult to reach and remote. Let's see now the principle of remote sensing. Remote sensing, as we've seen before, involves capturing data about the Earth's surface without direct contact. And this is done by using the electromagnetic spectrum, which is the full range of wave frequency emitted by solar radiation. Here you can see how solar energy interacts with the Earth, which is either reflected back into space or absorbed and then re-emitted as energy. Satellites, like the one shown here, detect this reflected and emitted energy to provide valuable information about our planet, including the detection of marine plastics. Although not energy can be captured by sensor, satellites are able to capture only a small part of the spectrum. Specifically, satellite can detect visible light, which is the same range that our eyes can see, allowing them to capture images in color. Beyond the visible light, satellites also detect infrared wavelengths, which is particularly useful for vegetation monitoring, for detecting fires, and also other thermal anomalies. Imagine now to look at the Earth through satellite eyes. Now, what is interesting here is that not all material reflect the light in the same way. And this is very important because it allows us to identify what we are looking at from space. So take a look at the graph here in the middle. What you're seeing is something called a spectral signature. And you can think of it as a fingerprint for different materials based on the light that they reflect. When electromagnetic radiation hits like an object, such as vegetation, water, or soil, some wavelengths are absorbed while others are reflected. A satellite sensor can detect these reflected wavelengths, and based on the pattern or signature, we can tell what the material is. So let's focus 1 second on the vegetation. Plants, for example, are really good at absorbing visible red light thanks to the pigments that they have in their leaves. On the contrary, they reflect in the green and especially in the near infrared light, which our eyes can't detect. So by studying the spectral signature, we can make even more informed decision about what's happening on the Earth's surface. For example, from tracking plant health to identify different land, but also to identify water bodies and eventually floating plastics. To continue, let's now explore quickly some satellite EO characteristics. Let's start from orbits. So orbits, there are different orbits used in satellite observation, each with a specific purpose. For example, the geostationary one, where satellites are placed in a way that they stay fixed over the equator at around 36,000 kilometers, matching the Earth rotation. In this way, they can provide continuous coverage of the same area, which is very perfect for weather monitoring and communication. Next, we have the low Earth orbit, and these satellites are much closer to Earth, which so usually around 2,000 kilometers above the surface. And because they're so close, they can capture high resolution imagery, making this orbit ideal for satellite imaging. Lastly, we have the polar orbit and sun synchronous orbit, and these satellites pass over the poles and are aligned with the sun, allowing them to revisit the same spots on Earth at the same local time each day. So like capturing an image of Paris every day at midday. Let's touch another aspect of satellite Earth observation, the type of sensing provided by the instruments. We have two main types, passive and active sensors. As we have seen before, satellites measure the radiant energy that is either reflected or emitted by the Earth's atmosphere system. This energy is then converted into useful data like temperature, precipitation, or soil moisture. This type of satellite are generally called passive sensors. On the other hand, active sensors generate their own energy for illumination. These sensors usually work in the microwave spectrum, allowing them to penetrate the atmosphere and operate under any weather condition, day or night. And these are very invaluable for meteorology, but also for the Earth's surface observations. Other key characteristics are the types of resolution in satellite remote sensing data. First, we have the spatial resolution, which refers to the smallest size of an object that a sensor can detect, usually indicated by the pixel size. The higher the spatial resolution is, the more detailed the image is, but it covers a smaller area. Next is the temporal resolution, which is how often a satellite revisits the same area. The spectral resolution focuses on the sensor ability to distinguish different wavelengths. So the higher a spectral resolution is, the more specific the wavelength range each band can detect. Lastly, we have the radiometric resolution, which refers to the sensor sensitivity to detect slightly differences in energy or brightness. The higher it is, the better the sensor is at distinguishing tiny variation in the data, which results in a sharper imagery. So how many satellites are out there? So as you can see from this image, our skies are quite full with activity, and there are currently thousands of satellites orbiting the Earth, each serving their unique purpose. Of these, about 1,000 are dedicated to Earth observation missions, and these satellites play a crucial role in a wide range of applications, from monitoring the weather to studying land use, and to track marine condition and also beyond. So let's move forward to the next part and explore the role of satellite technology and remote sensing in spotting marine debris in the ocean. So remote sensing overall is an effective way of tracking marine plastic on the ocean surface. And as we saw before, we can use different platforms, so drones, airplanes, and satellite, to monitor large areas and detect big patches of floating plastic debris. And this technology allows us to scale up what we observe commonly on site with in situ data and combine it with ocean models, making our prediction more accurate and reliable. And then let's now focus about the specifics of satellite remote sensing for observing and monitoring plastic from space. So compared to the other platform, satellite can keep an eye on much bigger areas, even those that are quite hard to reach with traditional on-site observation. It can fill the gaps where we don't have as many observation as in situ and give us a constant, regular and long-term data, which helps quite a lot for managing and clean up marine debris. Moreover, it supports better monitoring and policies for handling the problem. And finally, it can be a cost-effective and a replicable solution. In this field, several satellite missions equipped with different instruments have been tested and employed in recent years. However, we have to keep in mind that all existing satellites were designed and built for different applications without marine debris or biodiversity detection in mind. And this list include optical multispectral instruments such as the Copernicus Sentinel-2 and Sentinel-3 sensors. In addition, also commercial satellites such as WorldView, GeoEye, or PlanetScope. But also like hyperspectral missions have been used so far and tested, specifically PRISMA, which is a mission led by the Italian Space Agency. And furthermore, also active sensors have been demonstrated their potential for specific detection of marine plastic debris. But our focus remain here on passive optical sensors. In recent years, the Sentinel-2 satellite has been for sure the one mostly used for the detection of marine plastic, both in practical application and also in controlled experiments. It's important to note that initially it was not planned to be used for such application, but it was instead designed for terrestrial monitoring. But still, it offers a lot of advantages in this field since it's free of charge, has a global coverage, and offers a good trade between spatial resolution down to 10 meters and a revisit time of 5 days. Moreover, the multispectral instrument carried on board the satellite covers a range of 13 bands, including visible, near-infrared, and short-wave infrared. That is a range particularly suited for detecting and distinguishing small floating materials and debris on the ocean surface. Here we're showing satellite images of Sentinel-2, and as we learned so far, this image is basically a representation in 2 dimensions of the reflected sunlight spectrum reaching back the satellite. In this case, we are observing a true color image, so composed by the red, green, and blue bands that was taken on the 18th of September 2020 on the Gulf of Honduras. As you can see in this image, you're observing the sediment plume coming from a river and the aggregation of suspected material that might also contain plastic debris. So how do we identify and distinguish a floating object in a satellite image as the one we saw before? In remote sensing, this is achieved using different techniques, including the analysis of spectral signatures. That, as we saw before, is a unique pattern influenced by the object composition, texture, or structure that determine which part of the spectrum is absorbed and which is reflected. For example, areas covered by vegetation, water, and soil each have distinct spectral signatures. Water itself, as we saw before and also in this picture taken in the Gulf of Honduras, can have different signature depending if it contains specific material, for example, chlorophyll or sediments. Now that we saw the different patterns and spectral signatures of water, let's try to put it next to the plastic one and see how we can differentiate these two materials. And this differentiation is possible because this material exhibit a unique behavior when it comes to interacting with light. Plastic, along with various type of debris, stand out by being very much reflective in the visible part of the light spectrums. And this means that they bounce back a significant amount of visible light. But what is even more interesting is that they reflect also in the infrared part of the spectrum. And in contrast, clear water doesn't have this behavior. It absorbs instead infrared light rather than reflecting it. And this type of difference allows us to identify and distinguish these floating materials in satellite images. However, plastic debris is not the only material floating on the ocean surface and not the only one to be reflective in the near infrared part of the light spectrum. Here we are bringing an example of the spectral signature of sargassum, which is a macroalgae commonly floating on the ocean surface in a specific location of the ocean. But still we can notice a little difference. In fact, algae has a distinct and specific higher peak in the near infrared part of the spectrum, which sets it apart from both plastic and water. And this behavior in this near infrared region still gives us the possibility to differentiate floating algae, in this case from other materials such as plastic and from the surrounding water. So again, by looking not only at the visible part of the spectrum that our eyes can see, but also looking beyond at wavelength such as the near infrared, satellite sensor give us a unique perspective to performing this challenging task. Finally, to obtain a classification map as the one we see here, we use these properties by comparing the spectral signature of object in a satellite image to the spectral profile of material that we already know. Essentially, we are using the principle that objects with similar spectral signatures are likely to be of the same material or class. For example, in the image here of Honduras, by knowing the signature of marine debris and other materials, has been possible to classify and identify them in the satellite image. Later, we will see how remote sensing and machine learning techniques assist in automating this classification process and finally classify the satellite image. While the use of satellite spectral signature and machine learning for the detection of marine debris is quite promising, it comes still with a lot of challenges and limitations. And one of the main challenges is the presence of similar optical signals from other materials floating on the ocean surface. Plastic marine debris, in fact, is not the only one material floating out there. In fact, we also find objects such as wood, seaweed, or pumice rock. Moreover, some of these objects can be just as reflective as plastic. For example, sea foam and even ship or other type of structures. In the picture you see, we bring here an example of marine debris and foam. And you can see how they show similar reflectances in the visible to near infrared spectral range. So when we apply remote sensing techniques for classification and imaging, these challenges can introduce difficulties and errors and leading to false positive detections. While satellite technology shows so far a great promise, we need to be aware that certain factors can significantly impact the detection and monitoring of such a material. For example, here we are listing some physical factors, which including atmospheric conditions and sea surface effects. For example, cloud cover and shadows can obscure our view, and surface reflection can make the overall task quite tricky. Wind also can disrupt our observation. Sea surface effects, including, for example, the fact that some marine debris can be partially submerged, and the presence of waves, whitecaps, and sea foam can even complicate more the detection process. In addition to physical limitation, we also have to take into account some technical constraints of the platform and the sensor that we are using. For example, here we are showing like what is the influence of the spatial resolution. In fact, not all the plastic that is floating on the ocean is possible to observe, and it depends on its dimension and especially how it aggregates. A third limitation that can be listed is the possibility also of having available combination of both satellite imagery and ground truth data, which is not so easy to get. And this is quite crucial for enhancing the precision, the reliability, and the effectiveness of detecting floating plastic, especially to validate the information that we gather from satellite, ensuring that what we are detecting in the image aligns with the reality on the ground. To conclude this first part 1A of this course, here we are remembering that the fundamental aspect when using the satellites to detect marine debris is that we are primarily focusing on the floating part, which represent only a fraction of what is currently in the ocean. Additionally, due to the limitation that we saw before, individual pieces are impossible to detect by satellite. However, the situation changes when physical processes such as river plumes, currents, tides, and wind, and also vertical mixing, determine that individual pieces tend to aggregate into larger patches that satellite system can identify. So given the current state of technology, we are particularly interested in certain oceanic processes and coastal processes that create favorable conditions for satellite-based detection, allowing us to focus on these key areas for effective monitoring of marine debris. Here we are listing four different types of processes. One of them is the river discharge, so basically outflows of rivers into the ocean. Spills, so there's accidental and deliberate discharge of material in the ocean. The shoreline accumulation, where debris accumulates near the coastline, and convergence filaments, so areas where ocean currents come together and potentially causing an accumulation of debris.
Hi, Emmanuel, project developer at the Air Center. We hear the word artificial intelligence a lot these days, largely driven by the popularity of tools like ChatGPT, as well as the ethical issues raised by the use of AI. The fact is that AI plays a very important role in the field of Earth observation, allowing us to detect patterns, predict future changes, improve the understanding of data, and transform satellite imagery into actionable insights. AI enables computers and machines to simulate human intelligence and problem-solving capabilities. Machine learning is a subset of artificial intelligence that provides a system the ability to learn and improve from data and algorithms without being explicitly programmed. There are different types of machine learning categories, such as unsupervised learning, where the algorithm learns from unlabeled data, discovering hidden patterns from large volumes of data without the need for human intervention. In this MOOC, the focus will be on supervised learning, where the algorithm learns from labeled data. The goal is to predict outcomes for new data on a set of specific classes. A category from supervised learning very useful in Earth observation is classification. A classification problem requires the given dataset to be classified in two or more class labels, such as marine debris, ship, water, etc. From a large collection of classification algorithms, we will be showcasing the random forest. Random forest supervised models generate multiple decision trees during the modeling process and then combine their outputs to produce a final prediction. To be able to train our own random forest model to perform classification on satellite images of different features at the surface of the ocean, like marine debris, we will need an extensive dataset of spectral signatures, also known as spectral library. Merida is a state-of-the-art spectral library with 15 thematic classes and more than 800,000 pixel extractions focused on the detection of marine debris with Sentinel-2. Although the model presented in this MOOC was trained with the default spectral library, we also added to the dataset events of marine debris validated through different sources. The Merida dataset can be formatted as a CSV table, where we will use the spectral bands and spectral indices as machine learning features. The data is split into train, validation and test. We use the random forest classifier from Python scikit-learn to train the model. On this plot, you can see the mean spectral signatures from all classes from Merida. Marine debris is represented as MD. The obtained random forest model presents the following hyperparameters. To find the optimal hyperparameter values, you can use methodologies such as cross-validation on the validation split. N estimators correspond to the number of trees in the forest, max depth to the maximum depth of the tree. Other parameters can be explored in the documentation. The confusion matrix shows how many predictions are correct and incorrect per class. It helps in understanding the classes that are being confused by the model as other classes. See, for example, natural organic material and marine debris, but also ship and foam. These limitations can be reduced with other machine learning algorithms, with more useful data or applying masks. The Air Center developed a tool to detect suspected locations of floating marine debris and other ocean features, for example floating macroalgae, in Sentinel-2 satellite imagery using machine learning. Scan the QR code or enter the link to access Poseidon. There you will find all the information about how to set up an environment on your computer and start detecting marine debris on your Sentinel-2 images. Poseidon architecture can be simplified as the download of Sentinel-2 Level 1C images from services such as the new Copernicus Dataspace ecosystem, atmospheric correction using Acolyte, masking land, clear water pixels and clouds, and applying machine learning classification with one of the three models, Random Forest, XGBoost, or UNet. The tool is written in Python and Julia. Poseidon can be applied to post-disaster management or long-term seasonal analysis. In this MOOC, I will show you Poseidon's user inputs to obtain a classification image that will be opened in QGIS. In the Poseidon repository, you will find all the information you need for a correct installation. clone the repository using Git with the URL, web URL, or simply download the zip. Don't forget that you will need to register for free with some data providers. Here you can follow all the instructions, including the configuration. And when you run Poseidon for the first time, Acolyte and files will be downloaded automatically from GitHub. Also, files will download the CSV file with Sentinel-2 products metadata necessary to work with Google Cloud. You might encounter a Julia setup error. Please make sure you follow the dependency section related to Julia, which you can find in here. In this demonstration, the goal is to obtain the same results of the example. Open Visual Studio Code, or you can use other code editor to explore Poseidon. Inside configs and user inputs, you will find different options to play with. The search, for you to query Sentinel-2 products in the services catalog and create a list of products. Service, Google Cloud, or Copernicus data space ecosystem. Service options to apply filters to the search. ROI, your region of interest. NRT sensing periods to search products made available yesterday. Sensing periods, start and end date of interest. Processing, which includes different steps of the workflow, such as downloads for each product URL, atmospheric correction for each product using Acolyte, masking with different options of land, water, and cloud thresholds and buffers, and classification with options for the type of machine learning models, use of the CPU or GPU, and split of images into tiles or large regions for large regions of interest. The workflow also allows you to delete intermediate processing files and change the name of folders. After selecting the right user inputs, we only need to run the main workflow script. Let's speed the process. Finally, we can open QGIS. We can add a background layer. We open our Poseidon folder. And inside, we can open a stack, RGB stack. Adjust the bands. Selecting the minimum value and maximum value. and also the classification result. We need to go to Properties and select Color Palette. In here, the suspected marine debris is represented in the color red. After the previous demonstration, we'll leave you with some resources to explore more. We also provide some scientific publications of well-known researchers on the thematic of satellite detection of plastics. Thank you for attending this course.